Okay, in the blue packet that I just handed you, you'll want to remove the last page. The last page is notes. And due to the importance of the notes, I'm giving you this really nice sheet protector that you can put the notes in so that you will not forget the importance of those notes. So there you all go. You're welcome.
Thank you.
You're welcome. Oh, perfect even. Okay, so notes in the sheet protector there if you like. If you don't want to, your choice. So. Okay, look. Okay, listen. Okay, for this packet, I actually have, they're not posted to Canvas yet. I will post them soon. There are 8 videos of me going through examples, like 8 of the problems from the packet. So there's 20 total problems. 8 of them are on video if you need that extra resource. So in class today, we'll kind of jump around a little bit and do some of the problems from the packet. We'll try to avoid doing those 8 so that you have, in this video, a good number of discussions, and then you have the 8 additional discussions. Again, you cannot copy what I do. You have to understand so you'll be able to apply it to new problems. Somebody, I think it was Queston, asked about, if you go to Canvas, you'll notice that my feeling on this class for Canvas is that I don't want it to be complicated at all. It's just a simple list. All we do is just talk about ideas, and once you understand them, we give you a test to see if you really can, apply the ideas. That's what the AP test is all about. So my Canvas stuff is not complicated. It's not like go here, go here, go here, go here. It's just a list. Okay? And each day of class is shown. Therefore, if you miss a day due to illness or something else, you have at least some way to catch up. It's not the best. It's always better to be here. I've had several people who have been coming to different periods because they've learned quickly it's better to be part of the discussion than just watching it. But at least there is something if you're not here. And then you also have to go to Canvas and tell me that you are either in class or you've studied the video, and you also tell me that you've completed the homework. Once you've done that, the scores transfer directly to Skyward, and it's just a yes or no. There's no partial. So if you've done all of this, you've done all the certifications via Canvas, your Skyward grade will look fine. Otherwise, it'll look like you're missing things. So, and if you have trouble, you can come talk to me at my desk. So anyway. Okay, so back to the packet. Okay, in the blue packet, let's go to problem number 12 is a good place to start. Okay, all we're really doing in this packet is we're not learning any new concepts, really. I mean, maybe a couple of little things. We're mostly just putting together what you've already learned, and you're just learning to apply it in perhaps slightly new situations. Okay, so they give you a function, that's not new. They say identify the x-axis location of each discontinuity. Please memorize. You always look for the discontinuities in alphabetical order. It always helps. So, if you look at your blue packet, look at the notes. Item number 2 and 3 are key to getting us started. I believe item number 2 says, tell me if I'm wrong, that jumps only occur in piecewise functions. Okay, jumps only occur in piecewise functions. So you have that memorized when you're taking the test. You look at something like this and it says identify the x-axis location. You get to the line that says jump, you're going to write none. Because you'll say there's no way for this function f to have a jump because this function f is not piecewise. There's nothing else that you need to do. Just have that fact memorized. Please, Riley. So turn in the packet to number 13, Riley. So piecewise means multiple pieces. This has 3 different pieces. Does that make sense? Does that answer your question, Riley? 2 points. Anybody else? Okay, so we go on to the next one. We're supposed to find if there's a removable. Look at your note sheet. The note sheet has a couple of things about removable. One, the notes say that in the case of a removable, the overall limit will be different than the function's value at a given x. But there's also item 7 in the notes and item 6. Amanda Lindstrom left this nice sign here. It says, if you forget to factor, you fail. That seems harsh, but it is very accurate. Many times when we have a function, we have got to get the function factored so we can really see better what's happening. Without having the function factored, the problem becomes near impossible. So, I'm going to factor here. So I'm going to pull a 2 from the top. That's going to leave an x squared plus 3x plus 2. And we'll have an x plus 2 on the bottom. Questions from anyone? Okay, always better that you think with me, so raise your hand if you can see that the top can factor again. And you can see how to factor the top. Looking for hands. How does the top factor again? There we go. Let's go, Spencer. Try, stay with me. Everybody look. If you have a method that works, stick with it. This is the method I like. So I always just go piece by piece. So what goes here and here, Spencer? Let's pause there for a minute. Next place to always look is to go here. So what multiplies to make 2? So put a 2 and a 1. And now I have to make them add to make 3. That's what tells me whether I've got a plus or minus. So plus in both. 3 for Spencer for helping me. Who else knew it? Hands? Point. Okay. Questions? All right. Last thing I do, I've been doing this all year. I find it extremely helpful to break it up. I've seen many times on a test, a student will miss a question, they'll ask me what went wrong, I'll look at their work and I'll say, you didn't break it up. Once they break it up, they're like, oh yeah, and they know the answer. Okay, it's very important that you know this. This blue box is the formula for calculating all the y coordinates of the function. However, this blue box is exactly the same formula. You can use either one. This blue box here is the formula written using primarily terms. This blue box is the formula written using primarily factors. The factored version is easier to understand. Okay, so we're trying to look for removables. Item number 7 says you get a removable at any x coordinate where the y coordinate will become 0 divided by 0. So raise your hand if you can tell me. This is my formula for finding the y coordinate. Raise your hand, please. Is there an x value which will make that blue box become 0 divided by 0? Hoping for a few more hands. Looking for an x value which will make that become 0 divided by 0. Lots of people looking, but only a few people raising their hand. That's a little better. So Michael. So point, stay with me, Michael. If I plug in a negative 1, so I put a negative 1 here. That will make this equal what, Michael? So that will be 1. And then if I put a negative 1 here, what will, let's see, this equal here, Michael, on the bottom? So that'll still be 1. So then this green box will equal what, Michael? So then we got to put a negative 1 here. So then this becomes, what's this one going to be, Michael? So that becomes 0. So now we've got 2 times 1 times 0. So the whole thing will equal just 0 itself. So you got the right idea, but not quite what we're looking for. No worries. So so actually what we found was this. F of x is equal to 0 at x equal, 5 points for Michael for helping, negative 1. So f of x has what's called a 0 at x equal negative 1. That's going to come up in some future AP problems. It's just not on this one. Hannah, please. So help me, Hannah. So if I put negative 1/2 in for this x, and then I add it to the 2, what am I going to get? So we get 1.5 here. I put that negative 1/2 here, Hannah. What do we get on the bottom? 1/2 as well. So what's the green box? 1. Put the negative 1/2 here. This will be times 2 would be 3. So actually you get 3. So I plug in. Does that make sense? Yes? You good? You see it? It's got to make. You good? You do, but you're fine. So what's 1/2 divided by 1? Okay, I'm mixing up. You said to plug in what x? Negative 1/2. I'm messing you up a little bit. So negative 1/2 plus 1 is 1/2. Perfect. 1/2 divided by 1 is 1/2. 1/2 times 1 is 1/2. Times 2 is 1. So what you figured out was that when x is negative 1/2, the y value is 1. Did that make better sense? Good. So not what we're looking for, but you're good, right? Perfect. 5 points for Hannah. Who knows? We're looking for an x coordinate that's going to make the y coordinate 0 over 0. There we go. Isaac. So Isaac says negative 2. So stay with me, Isaac. What's negative 2 plus 2, Isaac? What's negative 2 plus 2? That's what we're looking for. The green box becomes 0 over 0. It does not matter what anything else is. Because 2 times, so the 2 times this 0 times whatever this is, the top's going to be 0. 1 times this 0 times 1, the bottom's also going to be 0. We have a removable discontinuity when the x coordinate is negative 2. 5 for Isaac. Raise your hand if you knew it before he said it. Point. Okay. Anyone want to talk about it? That's the idea. Looking for discontinuities. Vertical asymptote. Look at item number 8 in the notes. It says a vertical asymptote is an x-coordinate where the y-coordinate will equal a number divided by 0. Okay, for this class, we don't have any overlapping discontinuities. So because we know that the green box is what we're focused on when we identified the removable, we don't really look at that any longer when we're looking to see if there's a vertical asymptote. It's still there, but that's what's causing the removable. We're looking to see if there's any other x that can make the denominator 0. And there's no other x's in the denominator, so we do not have a vertical asymptote. questions? So I'll ask you a couple things, Taryn, so it'll stick better. Is that okay? Are you comfortable that this blue box is how we find the y coordinates? Awesome. Are you comfortable that at an x value of -2, we have the removable? Awesome. So we don't look at this and say, oh, well, that could be a vertical asymptote because if the x is -2, I got a 0 on the bottom. Like, that's too simplistic. Don't think of it that way. This green box is causing the removable. But there are no other x's in the denominator. So there's no other x value I can pick that'll somehow make the bottom of this whole formula 0. So since I can't make the bottom of the whole formula 0, no other vertical asymptote. 2 more points. Anybody else? Solid. Okay, part of this worksheet is just making sure you're not forgetting the idea of limits since it's all connected. So we are supposed to find this limit right here, which means we're supposed to find the left and right limits. We're supposed to find the limit when x is a little bit less than -2. And we're also supposed to find the limit when x is a little bit more than -2. So we are supposed to do both of them. With a non-piecewise function, you can usually, not always, but usually find the left and right simultaneously. You simply look at the formula and ask yourself, here's my formula. If my x value isn't equal to -2, but it's close, what am I going to get? So let's start over here. Raise your hand, think with me. If I make this x almost -2, not exactly, but almost, please raise your hand and tell me, what will this become? The green circle when x is almost -2. Hands up. When x is almost -2, what's the green circle, Rachel? Very, very, almost, perfect. Very, very close to -1. Who knew it? Point 2 for Rachel. So here we have almost -1. Raise your hand. What's this going to be when x is almost -2? What's that circle when x is almost -2? Paisley. So this green circle is almost 0. It's maybe something like this. It's tiny because it's almost 0. But it isn't 0. Show me your hands if you knew that this was going to be almost 0. Show me. Point 2 for Paisley. Anyone want me to talk about it differently? Okay, raise your hand, please. What's this going to equal when x is almost -2? Hands up. There we go. Let's go, Chris. And how is this almost 0, Chris, related to this almost 0? They're exactly the same, hence we get a ratio that is exactly equal to 1. So when the x-coordinate is almost -2, we don't get 0 over 0 anymore. We get 1. Okay, that difference you will always be tested on the AP test. So you must understand the difference. When you plug in exactly -2, this is exactly 0 over 0. You plug in close to -2, that is now 1. Questions? Please. It's okay. Let me ask you a question so it will click, hopefully. So, John, if we plug in exactly -2, what's this? Perfect. How about this one? 0 divided by 0 is undefined. Okay? If we plug in, say, 7, what do we get? What do we get on the bottom? So what's the whole thing? Well, it's 9 over 9, which is 1. 9 over 9 is the same as 1. So if we plug in close to -2 here, what's this? depending on whether we plug in something that's a little more than -2 or a little less. But either way, it's going to be really small and close to 0. But the key is what's going to happen to the bottom. Same thing. So what's this going to equal? It's 1. Does that help? Okay, look here. 2 for John. Look here. Listen. Okay, you must memorize. You must memorize that this green box that I've now colored in so much because it's the video and I want to make sure they can see where I'm pointing. Okay, that green box is always equal to 1, except there's only one exception. Hands up. What's the exception? Hands. Like that is equal to 1 for any x you pick, except. And that's what you have to have memorized. Kate Crofts in the back. -2. If this x has a value of -2, we do not have the green box equaling 1. The green box is undefined. It's 0 over 0. You must keep track of that difference. Questions? Okay, so this limit, let's see, when we go close to -1, close to -2, this becomes 1. This becomes very, very close to -1. -1 multiplied by 2, this becomes very, very close to -2. That's the value of the limit. We did the left and right. We just kind of did it mentally. Because we did this, Taryn. We said, this is always 1, unless x is exactly -2. But for limit, x will not be exactly -2. So this is definitely 1. Coloring getting thick there. We focus on this. Taryn, if my x value is slightly more or less than -2, in either case, what will this be very close to equaling? -1. So we really are checking left and right. Yes. There you go. Does that make sense? 2 more. Okay, cool. Raise your hand, please. What goes here? Hands up. What goes there? Hands. Show me. What goes there? Parker. How many agree with Parker that a 0 goes here? Okay, we're going to give yourself 2, but you're incorrect. So let's get the right answer. What goes here? What is the y coordinate when the x coordinate is exactly -2? There we go. Let's go Ruth. Undefined. When you plug in exactly x equal -2, you get 0 over 0. Rachel, please.
So 0 over 0 is undefined.
Yeah. And just memorize that one, Rachel. I don't have a really good explanation for a y on that, to be honest. 0 divided by 0, undefined. Any number divided by 0, also undefined. Any 0 divided by a number, that's 0. That's what we got here. 2 for Rachel. Soraya, question? No? Okay. Anybody else? Please.
When you're looking for a removable discontinuity, why are you looking for an x coordinate that equals 0 over 0? I guess you could just memorize that.
It all comes back to this idea here, Marielle, that when we have this expression that's actually always equal to 1, except for one x coordinate, that's what causes this to occur. It allows us to find the limit on either side, like really, really close to x equal -2, but then right at x equal -2, suddenly we don't have a function value anymore. That's what causes the removable to occur, because this is the definition of removable. That helps. Okay. Anybody else? Perfect. Okay, so that's example 12. Problems 1 through 12 in the packet are asking you to do exactly the same thing that we just did with 12. Like nothing different than that. problems are different, however, but the basic analysis follows the similar logic. Let's jump to, look at 13 through 20. Okay, if you read the instructions at the top of 13, it says you're supposed to be finding the value of a and b so that the function is continuous. So this is something they do on the AP test all the time. Go to number 14. They give you a problem that's backwards. 12 was a forward problem, meaning they said identify where the discontinuity is located. 14 is a backwards problem. They say, no, go find a value for a and b so that this thing is continuous, so that it doesn't have any discontinuities. Whenever I solve unknown, new, backwards AP problems, it's going to feel like I'm just wandering around. Like I'm like, hey, well, let's try this, let's try that. You have to get used to doing the same thing. It's actually a very realistic thing when you're doing something in a real life situation where your boss says, hey, we want to develop this product and you're going to spend the next year doing it. You don't just sit down and say, oh, we're going to do this, then this, then this. You wander around for a while and you're like, kind of think about it, try this, try that. Same thing happens here, just on a much smaller scale. So here we go. First note I would pay attention to is this. As I said earlier, I think Amanda's advice to, always factor. But there's nothing that factors here, so that's not going to help. So I skip that idea. I'm like, okay, I remember us talking about in class that if there's going to be discontinuities, we should check for them in alphabetical order. So jump, then removable. So my thought is let's kind of play around and see if we can find if there's a jump. If there's a jump, we need to eliminate it because we're supposed to make the function continuous. Questions about anything so far? So I remember another note, note 2 in your list that says jumps only occur in piecewise functions. Then I remember note 3 because I'm taking the test. I don't have any notes in front of me. Note 3 says jumps only occur at the now I spelled it wrong. It looks like transitions. I can't even say that word. It's supposed to be transitions, not transitions. But anyway, sorry about that. Transitions. The transitions of a piecewise function are easy to identify. They are the x-coordinates where you change from one formula to another. So at a certain x-coordinate, we stop using this formula and we start using this one. At a different x-coordinate, we stop using the middle and we start using the bottom. So raise your hand if you can tell me, what are the x-coordinates of the transitions that are known as the transitions? Hands up. Look at the piecewise function. You look at what they're giving you and you can identify the x value when you stop using this and start using this. The instructions are here. They're telling you what x's to use. They're saying what x's get used for this formula versus what x's get used for this formula. So what are the x values we are concerned about with relation to jumps? Got about 2/3 of you seeing it. Maddie?
Would it be 2, 0, and 4, 0?
So all we really care about is the x-coordinate. So the 2 and 4. So the transitions, spelled better, at x equal 2 and x equal 4. How many saw that? Point. Okay. You would need more explanation. Talk to me, Rachel. Just not seeing it. So the way you read this formula is you say, if I want to find, are you comfortable, Rachel, that this formula is how we find the y values? Yeah. Okay. So you're okay that we're going to use one of these three to find every y value. Good with that? The way we figure out which of the three to use is we look over here. So the top one, the blue, that gets used for any x that is 2 or less. So like if I'm using x's that are any of these, and a bunch of others, they'll all use the blue formula. Then I transition to a different formula. So if I've got x's that are bigger than 2, right there, bigger than 2, like say 2.1 or 3 or like 3.5, they all use this formula. Does that make sense? Awesome. Do you see it now?
Well,
Keep going.
what's this
Transition. I'm just saying, it's really just my word. Like I've never seen it in a book. I'm just saying it's when we change from one formula to another. Like you could call them the change points, or I don't know what word you want to use. It doesn't really matter. They're never going to ask you, they're never going to use the word transition on the AP test. I just had to have a word that I could use to explain to all of you. And it's this X here. Like when I stop using the blue and I start using the purple, that's happening at X equal 2.
Oh, I see. Okay.
So I said I'm transitioning from one formula to another. Okay, you're good. 3 points for Rachel. Anybody else? Look like you were taking her like a thermometer. I noticed. When she did it, I'm like, practicing to be a nurse. Okay, please, Chris. So, Chris, are you comfortable that we use the blue formula to find all these y's here? Comfortable with the purple? We start using the very bottom one, the green one, when x is bigger than 4. So that's the other x value when we switch from one formula to another. Is that your question? Okay. 2 for Chris. Questions? Cool. Okay, look at your notes. The notes say jumps can only occur at the transitions. Those x coordinates are 2 and 4. So therefore, we want to find out if there's a jump. So you remember, you have this memorized, which says you now want to check the left and right limits at those x coordinates. So that's where we go next. We say the limit as x approaches 2 from the left. Raise your hand if you know that. Go. What is the limit of this function as x approaches 2 from the left? Hands up. Pretty decent sampling. Question? That's the formula we want to use. So we're trying to look at an x value that is a little bit less than 2. So we're using this formula, x is less than 2. We're replacing the x with something that's very close to 2. So question, close to 2 plus 1 is close to 3. Close to 3 squared is close to 9. And then we have to multiply by the a. So what I was hoping you would say is, we don't know what a is, but we do know that if we find that left-hand limit, we get a value that is 9 times whatever a is. Raise your hand if you knew that before I did it. Point. Okay. That's the idea. Questions? Please. Everybody look up. It's not the line under the big alligator. Actually, I think of it as an L, to be honest. L like that. X is less than 2. That's how I remember it. The alligator never helped me. I don't know. It's like, great, there's an alligator. How does that help? Anyway, it's not the line. Look at me, come on. It's not the line. The line says x is equal to 2. I'm using the purple formula because I need when x is slightly less than 2. Good question. 2 for Chris. Anybody else? Please.
I might just be tripping, but there's not an A before the first formula on factors. We're on 14, not 13. Oh, yeah.
Tripping. All right. No worries. No worries. Just keep asking. Keep asking. 2 for Luke. Anybody else? Okay, cool. We found the left-hand limit. If we're looking for a jump, we have to find the right-hand limit and compare them. So, please find the right-hand limit. The limit, as x approaches 2 from the right, hands up. There we go. Let's go Harrison. Harrison votes for 18. Who would support Harrison? Point. We want to talk about it. Please. 18. So question. You're okay that we're checking the left and right limits? Okay. So we've got to go, limit means for this x value, go find the y coordinate. So we look over at our formula and say, question, do we use the top, middle, or bottom formula when we have an x value that is slightly more than 2? Which one do we use? It says right here, if x is more than 2, you got it now? Good work. 2 points. Anyone else? Don't let stuff go by. Talk to me if it's not clicking. Okay, cool. These two limits are not the same. That means we have a jump. But the goal of the problem is to make sure we don't have a jump. Hands up. What do we do? This is AP. This is exactly the AP test. Like, this is a weird problem. I've never seen this before, but like, eventually it kind of makes sense, and you just keep working at it. Haley, Pedroza. We make A equal to 2. If we make, hey, how many saw it? Point 2 for Haley. If we make A have a value of 2, we have made sure there is not a jump right here. There's not a jump at x equal 2. That's the goal of the problem. Get rid of the jump, if there is one. There may not have been one there, but that's, questions. Chris, please. So now we have to make sure there's not a jump at the other transition. 2 points for Chris. The excitement is palpable. Yeah, all right. So we do the other limit again. So here we go. Ah, 4, sorry. Okay, show me your hands. What's that? Come on, think with me, don't watch. Hands. What's this? Come on. There you go. Luke, what do we got? Raise your hand if you agree with Luke. Point for the other person who agrees with him, whoever that was. 2 for Luke. Questions? What do we do now? Hands up. The idea is not to follow me, it's to think ahead of me. Nate. Find the right-hand limit. 2 points for Nate. Ashton. Show me your hands. Who knows the answer to the right-hand limit? The blue. There we go. Let's go Kate Spencer. Who agrees with Kate's? Point 2 for Kate. So now what? Hands. There we go. Nope, that's exactly right. The idea is to find the value of B so that we don't have a jump. So we know that everything's working great. Trying to get somebody new here. Hannah. So what would B equal, Hannah? How many knew it? Point. Okay, 2 for Hannah. Okay, so we found the value of A and B that gets rid of the jumps. Be aware that in future, some of the other homework problems, you might be worried about a removable. Okay? Might be worried about a removal. In fact, let's have any time for that. Let's do an example that has something like that. So go to number. Let's go to 18. Points if you can think what I'm thinking. Hands up. I read the problem. I remember what I have memorized, which in this case I've helped you because I've got it all in front of you. What am I thinking? The goal is the same. Find A, no B here. Find A so that this function is continuous. So I'm trying to remember all these key elements and try to figure out a place to start. Let's go down. If I forget to factor, I'm going to fail. Raise your hand if you knew that's what I was going to do. There we go, point. So I factor it out. So let's see, I'm going to get x. Now let's do some work over here. So it's going to be x. It's going to be x squared minus x minus 12. So that looks like it might factor again. Hands up if you can see how to factor that again. Really big clue. Not always, but most of the time when you're factoring, you're looking for stuff top and bottom that will match. So if you can see how to factor the bottom, it gives you a clue as to how to factor the top. That's almost always the case. Hands up. How do I factor the top further? Riley? X plus 3, x minus 4. Show me your hands if you saw it before Riley said it. Point. 2 for Riley. Anybody? Solid. Hands up. How does the bottom factor here? Hands up. How does the bottom factor? Show me hands. Let's go, Amelia. So I get 4 times x minus 4. How many knew it? 0.2 for Amelia. Yeah, that's the clue there. Is x minus 4 was the factor. So now I can come over here and say that my function f, this is what I mean by kind of wandering around. Like I haven't solved anything, but I know from experience, and I'm telling you, I'm sharing my experience with you, that if you factor, it becomes easier to see what's happening. So I haven't solved anything, but I should be in a better place now. So let's see, let's break it all up. So I'm going to get x over x. I'm going to get an x minus 4 over x minus 4. Oh, you're right. Thank you. Boy, that was dumb. How many saw that error? Hands up. 2 points. Take 3, 4, take 5. Okay, I'm serious. Write down 5. That was really bad error. F of x equals, okay, gotcha. So we have a 1 over 4. We have an x over 1. We have an x subtract 4 divided by x subtract 4. We have an x plus 3 divided by 1. And that's all valid for all x's except 4. Questions there? Please. Absolutely. Good question, Michael. All I'm trying to do is write out all of the factors separately so I can just see them better. So what I did is I said in the numerator, there's a factor of x. So that's right here. But there isn't a factor of x in the bottom, so I just put a 1 instead. Keep going, or are you good? Okay. Right. That makes sense? Yeah, and I do the same thing on the top. Like there's a factor of 4 in the bottom, no matching factor to go with it, so you just put a 1. Good question, Michael. 2 points. Anybody else? Okay, let's see. Then we know that this is A whenever x is equal to 4. Okay, so we're factored. Goal of the problem is make sure the function is continuous. So first discontinuity to check for is a jump. So we want to check the left and right limits. So we want to go find out what the limit is as x approaches. What x am I concerned about? Hands up with regard to a possible jump. What x would I be worried about if I'm worried about a possible jump? There we go. What x am I worried about? Let's go, Parker. 4. Who agrees? Point. So that means I check the limit, 2 for Parker, as x gets close to 4 from the left. Here's how I do it. Say it out loud, please, together as a chorus. To find this limit, when x is slightly less than 4, do I use the top formula or do I use the bottom? Ready? Say it. Top or bottom? Say it. Top. Everyone clear? Okay. So I use the top formula. Here's how I use it. This is going to be 1/4. This is going to be very close to 4. Say it out loud. What is 1/4 multiplied by close to 4? Say it. Say it one more time. That was weak. Close to 1. I have 1/4 exactly. I have an x that is close to 4. So close to 4 multiplied by 1/4 is close to 1. Question. Okay? When I put an x in here that is close to 4, raise your hand, please. What's the green box? Hands. Come on. When x is close to 4, what is in the green box? Lily. 1 exactly. Not close. 1 exactly. How many knew it? Point. Okay. 2 for Ruth. You need me to talk more about it. We did it earlier.
Why did it do that?
So the idea is, Luke, if I put in a value that's close to 4, and I subtract 4, what do I get? Close to 0. What's happening to the bottom? What's going to happen here? Right, so you get, no, it's perfect. You get exactly the same, both top and bottom are close to 0, but together they divide to become exactly 1.
And then if we had exactly
Undefined. Yes, memorize again. Hey, I mentioned we had to memorize it earlier today. When you have this situation in the green box, it's going to happen over and over again all year long. That is equal to exactly 1 for every x, except x equal 4 itself. Okay? Cool? Okay, so we got this far. This is equal to very close to 1. This is equal to exactly 1. You multiply those together, you're close to 1. Hands up. What will this be when x is slightly less than 4? Hands up. What will that be when x is Anna? So Anna, stay with me. So we have close to 7 multiplied by what, Anna?
1.
So we got close to 7 times 1 is? Close to 7. This is, so close to 7 times close to 1 is close to 7. 3 points for Anna. Question? Okay. If that argument all made sense to you, you should be able to raise your hand and tell me what this is very quickly. What's the limit as x approaches 4 from the right. X is slightly more than 4. Hands up. What's that limit? Hands. Come on. There we go. Soraya. Who agrees? 2 points. 3 for Soraya. 2 for the class. So go, please.
Then would A be undefined because if x equals 4, then it's 0 over 0 is the removable discontinuity?
Oh, you're on the right path, Maddie. You're just making a small error. Stay with me for a second. First question, hands up. Why did we do all this? Like, what was the purpose of all this? Hands, come on. Why did we do that? What's the why? Nate. How many knew it? Point. 2 for Nate. Looking for a jump. Please say yes or no. Is there a jump? Yes or no? Say it. No jump. We move on. So now we're exactly where Maddie said. We're looking to see if there's a removable. Well, we know that the overall limit as x approaches 4 is exactly 7. Fair? A removable occurs if the overall limit and the function's value are different. A removable occurs if the overall limit and the function's value are different. So raise your hand, please. What's this? We're just stumbling around here trying to figure this out. What's the value of the function when x is equal to 4? Hands up. What's the black? Just read the formula, Maddie. What's the value?
Would it be undefined or would it be 0?
Here's the difference. If you're looking to find f of 4, Maddie, do you use the top formula or the bottom? So this is telling you, you're okay. Look. This is telling you that you're only allowed to use values of x that are not 4 when you use the top formula. This says use the bottom formula when the x value is exactly 4.
Oh, okay.
So what goes here, Maddie? So what goes here?
4?
No, but that's okay. So we're using the bottom formula. The bottom formula says when x is equal to 4, the y-coordinate is a. Questions? Hands up. What do we know? We just learned something. There we go. What do we now know? Like you put it all together. Put all the pieces together. AP test, classic. You do a little this, a little of that, and you go, oh, wait a minute, there's a connection. Rachel, what is it? So there is a removable right now because you're perfect. Because we know that the overall limit is 7. We know that the function's value is a. That is definitely a removable discontinuity. The goal of the problem, too, for Rachel, is to make sure there isn't a removable discontinuity. Hands up, so what do we do? What's our conclusion now? There we go. Caitlin in the back. We want to make A 7. That's the conclusion of the AP problem. Make A equal to 7. We've now used, hey, people always ask me, how do they make AP problems different? This is a great example. Like it uses all the knowledge you've learned over the past several days, but in a new way. That's what they do on the AP test. So I can show you that they've done this before, but the trouble is this year they'll do something else that's different than this. Okay, but that's the general idea. Questions? Please. You okay if I get you to say it? It'll click better.
So I thought it was that the limit and then the overall limit is 7.
So you're good there, Luke, right?
But then why does A?
So are you comfortable that the goal of the problem is to make the function continuous? Okay, no one talks, so I can talk to Luke. You're okay. Hey, shh. Hey, don't talk. I can't. The video will be really messed up too.
There's no jump. The limit equals.
Right, left and right limits are the same, so no jump.
We only go to removable, but
So what? No, you can answer this. So what are we checking to see if there is a removable discontinuity? What do we test? according to the definition.
So we check if the limit is used for x, right?
Right. So do we know this?
Yeah, we know that, but we don't know x,
Very good. So what's the limit?
right? Oh, so we just put a as 7, then we do 7.
Slow down for a second. So what's the limit?
The limit is 7.
Awesome. Then what we did next is we said we need to go find f of 4. Don't get confused. This a is different than the a in the problem. That's just whatever x we're using. So we've got to go find f of 4. So we read this and say, according to the formula, the y-coordinate when x is 4 is always a. But we don't want a removable, so we want a to be the same as the limit, there we want a to be 7. I'm not sure that clicked at all, though. Not really. Fair? Sort of. Whole class, everybody answer this. In order for I don't know how to say it. We do not want there to be a removable discontinuity. Okay? So we want the y-coordinate when x is almost 4 to be exactly the same as the y-coordinate when x is 4. That's the goal. We want the y-coordinate to be, when x is almost 4, be exactly the same as when the y-coordinate is 4. So raise your hands, please. In this problem, before we did anything, what is the y-coordinate of this function f when the x-coordinate is exactly 4? Like before we did anything, when all you could look at was this. Hands up, come on. If you're just using this, what is the y-coordinate when the x-coordinate is exactly 4? Let's go to the, hold on, getting the names here. Shoot. Julian. But what is the, so up here, I gotta make something else. Hold on a second. Gotta make a table. Here's what we're doing. You have x, you have y. I told you on the very first day of class that every single calculus problem is nothing more than understanding how x relates to y. If you always go back to the fundamentals, it always helps. So Julian, one more time. If we have got an x-coordinate that is exactly 4, according to our formula for f, what is the y-coordinate? Raise your hand if you understand what Julian just said. Perfect. Point 2 for Julian. What is the, according to our formula, hands up. What is the y-coordinate when the x-coordinate is slightly less than 4? It's all about the x's and y's. It's all it is. It's all we're doing. Let's go, Grace. We use the formula, and what did the formula tell us, Grace? That the y-coordinate would be when x was slightly less than 4. Raise your hand if you understand what Grace just said. Point 2 for Grace. Hands up. What's the y-coordinate when the x-coordinate is slightly more than 4? Getting new people here. Oh, I think I've called in every single person in the room today almost. There we go. Katie, sorry. Who understands? Point. So, 2 for Katie. But we want all 3 of these to be the same. Because if these 2 are different, we have a jump. If they're different as written, we have a removable. Like when these 2 are the same, but the one in the middle is different, that's a removable. We want them to not, we don't want that. So we know that the value of A must be 7 to prevent any removable discontinuity. Please. What we really had is this. This is what we had. That's really good, Isaac. Hey, look, think back to earlier graphs. We start with something like this. Now the numbers are, well, that's actually pretty close because we're at x equal 4. This scale is not quite right. we found this value right here and this value right here to be, hold on, let's have you raise your hands. So in the problem we are currently discussing, raise your hand. What did we find the y-coordinate of the red and blue dots to be? Hands, come on. In the problem we are currently discussing, right here, what did we find the y-coordinates of the red and blue dots to be? There we go. Let's go, Marielle. How many agree? Point, 2 for Marielle. So that's what Isaac's saying. That's what we had. What did we find the y-coordinate of this dot right here? See, the x-coordinate of that dot is 4. Before we did anything, hands up, what was the y-coordinate of that dot? Before we did anything, like just as the problem was given to us, what was the y-coordinate of that dot before we did anything? Question. Raise your hand if you knew that that was going to be A. Point, 2 for question. And then we did what Isaac said. We said, no, we can't have that. That's a removable discontinuity. So we make A's value 7, we fill in the hole. Is that what you meant? Perfect. Like we move it. The dot moves. So. Questions? Luke, better? Okay. Anybody else want to talk? Cool. Next thing. That is a really good example of what I've been trying to impress upon your mind, that's the AP test. Okay, it's not do something you've done before, it's use the concepts you've learned to do something else. And it does feel a bit like you're stumbling around, but that's where you've got to have all those facts memorized so you kind of know where to stumble. So, okay, cool. Let's do another one. Let's go back to here. Six is good. We haven't done 6 today, right? Have not? Okay. Okay, we're going to stumble around a little bit. So I look at the board and I say, okay, I got to find, oh, hello. I got to find, I'll get it. So I got to find if there's a jump. You're welcome. So, hey, right away before I do anything, I already know there are only 2 possible answers right here. Only 2. Raise your hand if you can read my mind and know what I'm going to put inside those boxes. There we go. Looking for a jump. Only 2 possible answers. Spencer Olson. Raise your hand if you understand what Spencer just declared. Point. 2 for Spencer. We want to talk about it. Solid. Raise your hand. How do we determine whether there is a jump at 1 and whether there is a jump at 4? Hands up. How do we know whether there is or is not? There we go. Nate. Yeah, so the worksheet kind of cheats. Like on an actual test question, they're not going to have, go find the jump, and then, oh, by the way, why don't you find this too? Like they're cheating, right? They're kind of telling you what to do. But that's what we've got to do is find these 2 limits. That will tell us whether or not there is a jump at 1. Everybody good on that? So raise your hand. What goes here? Come on. Do it with me. Hands up. What goes there? There we go. Thinking with me. Don't ever just watch. Do it with me. You do far better. Luke on the front. Hands up if you agree. Point 2 for Luke. Keep going. Next one. Rolling here. Stop me if you're like, I don't see it. Just got to stop me. Oh, please, Riley. Oh, you're good. Who's ready for the green? This one here. Go, come on. This one, change color. Green. What goes on the green line? There we go. Let's go, Haley. Who agrees? Point. 2 for Haley. Hands up. What do we know? Stumble around, then we make a conclusion. That's how the AP test works. Stumble around, then you see a connection. Oh, wait a minute. I know something now. What do I now know, Riley? Yeah, so get rid of this. No jump at x equal 1. Okay, 2 for Riley. Because the left-right limits at x equal 1 are the same. Please.
We also know that the overall limit is 5.
Nice. Nicely done, Maddie. 2 points there. Hands up. What's f of 1? So now what do we know? Hands up. Now what do we know? We got 3 minutes left in class. Hannah Bartholomew. At x equal 1, this function is continuous. Therefore, there's no removable at x equal 1 either. We'll just do a little cross out here so we remember. No removable at x equal 1 either. Perfect. 2 for Hannah. Questions about anything? If you're struggling to keep up with the class, the only way to fix it is you got to come after school. Like, there just is no other way. Like, if you don't fix it now, it just gets worse. It is like a infected sore. Gross is the right word because that's how it will feel as it gets worse. Like, it just, I promise, it just becomes this, yeah, it has to be treated quickly. Okay, hands up. Let's finish for the bell. What's this? Go, blue line right there. There we go. Soraya? Raise your hand if you agree. Point, 2 for Soraya. Do this one now, red. There we go, Rachel. Oh, you're good, no bad. No worries, I get you, you're okay. Chris. Chris boldly states 21, which is different than 20. Who agrees with Chris? Point, 2 for Chris. Hands up, what do we know? Hands up, what do we now know? Katie. Nicely done. We found a jump at 4. The overall limit is non-existent. Undefined, to me, kind of same thing, but they'll say that. They'll use this word. 1 second, Taryn. All eyes, look. For our class, you're never going to have overlapping discontinuities. So because we know that there is a jump at 4, you know there is not a not a removable at 4. They don't overlap. You don't have them in the same place. Got it? There's no other transitions, so the only other thing to worry about is something like this. But there's no way for our formulas to ever have a 0 on the bottom. So we're done. There's none of this. All we have to do is answer f of 4. Hands up. What's f of 4? What's f of 4? The idea here is to see the connections, not do the work. Grace. Terry, did you have a question? You're okay, just making sure. Very good. 2 for Grace. Cool, the bell's going to ring. Good work. That was awesome, man. That was solid. That was good work.